Okay, cool. Well, all right, everyone, let's get started. I'll introduce Kenneth. We're very fortunate today to have Ting-Hao. Is that how I pronounce it?
Yes.
Ting-Hao. I always know him as Kenneth Huang from Penn State University, where he's an associate professor. He did his PhD at LTI at CMU, which I think most people in this room are familiar with, and his undergrad and a first master's at National Taiwan University in Taiwan. You'll notice that if you know anything about CMU, they actually do have an HCI department and their NLP department, LTI. And Kenneth did his PhD in LTI. So he is kind of like right at the intersection between human computer interface and NLP. And I think you said that you want 50% of your papers to be in STAR CL conferences and 50% in a perfect world and 50% to be in HCI Chi sort of conferences. So it should be an interesting talk, really talking about where the frontiers are and how we get data. So let's please welcome Kenneth.
Thank you. Thank you for having me here. So today we're going to talk about data annotation, crowdsourcing, and of course, large language model. All right. So before I get started, I kind of want to say thank you. So I actually saw a few of you last week. So Penn State actually hosted the MASC Mid-Atlantic Student Colloquium Saturday last week, less than a week ago. And this amazing conference was initiated and funded by people at Johns Hopkins. So I really thank you for inviting us to host this event. We were a little bit worried that no people will show up because we are in the center of Mid-Atlantic area. And it turns out we had over 100 people, luckily, actually show up, and we gave amazing ice cream, and we had 64 posters, and we have 4 oral presentation and 3 keynotes. So thank you for basically initiating this amazing thing, and thank you for inviting Penn State to host this. This is actually the first time we host this particular event. So thank you very much.
Thank you for hosting.
Yeah, thank me for yeah, and thank you for coming. Some of you actually show up. Thank you very much. All right, so this is me. So I am now an associate professor at Penn State University, and just like Kenneth just said, my work, we try to focus on the intersection of NLP and HCI, natural language processing, and human-computer interaction. What we mean by that is that we really try to publish at HCI venue, hopefully half of our papers, and also NLP conferences, right? So what I am interested in mostly is the human problem in language technology, in particular, how people use language technology, or how we can create new language technology or capacity to fulfill people's need. That's what I do, right? So, and because of that, because of this kind of drive, I did create a lot of data set, and my student also created a lot of data set. Actually, my entire PhD dissertation focused on using Mechanical Turk to do something really cool, right? These are just a few more representative, famous ones that we created along the way. So one earliest and probably one of the most famous one is the visual storytelling data set. So this is an example you can see. This was the first data set that can actually focus on creating basically we collected 10,000 small photo sequences, and we have Mechanical Turk workers to sit down and write short stories for those sequences, right? That's visual storytelling data set. And back then it was trying to basically create a model that can basically generate short story from a sequence of images. And this one at the right bottom corner is called CODA-19 dataset. This is also crowdsourced, and basically it's a sentence classification dataset. We have people to classify sentences in paper abstracts into different aspects. Is it the background sentence? Is it a purpose sentence? Is it a method sentence? Is this a finding sentence? That's another dataset we created. And here, we also last year at ENOP, we also created this data set we call CocoLofa. It's a data set that try to have crowd workers simulate the news comment section. And we basically specify as crowd workers say, hey, can you write a comment? that embodies this very particular logical fallacy. So because what I do, I try to create different data sets, and often enough is to introduce new capabilities, or at least to test new capabilities of language models, right? And this is at a very high level. This is, of course, oversimplified version. Many of those data sets were created using crowdsourcing platforms such as Mechanical Turk. And at a very high level, this is how it works, right? It's you, like requester, researcher, developer, decide, okay, what I'm going to do, what I'm going to collect. And I figure out, okay, what data I'm going to label and what label scheme I'm going to use. Often enough, you need to develop your own label scheme. And then you send all that, send data, send label scheme to crowd workers, and eventually you get your data labeled, right? So over around 10 years, past 10 years, I have been doing this for many different projects. Well, and about 2.5 years ago, this happens, right? So in 2022, in November, ChatGPT suddenly becomes publicly available, so it becomes much easier to use large language model. And this incident triggered a lot of things in our society, of course. In particular, in the world of crowdsourcing, this incident basically triggered a set of genre of papers that compares ChatGPT and online crowd workers. These three papers are probably one of the most famous ones, like ChatGPT outperforms crowd workers, large language model outperform crowd workers, and ChatGPT outperform crowd workers, right? So those were really popular back then. And imagine you have been working on something for decades. You spend a lot of time, a lot of effort, a lot of money, a lot of your life working on crowdsourcing, and you kind of consider yourself a master for crowdsourcing. And suddenly someone come with this really powerful, flashy thing and come to you, say, we can do this better than you, right? And what do you think? Well, you enter the denial phase, right? And so there are, for good reasons, there are reasons crowdsourcing experts have some complaints, or at least have some concerns about those papers. So most importantly, these papers heavily focus on comparing average individual crowd workers' labeling ability against large language model, right? And because of that purpose, it's a fair purpose. They did something sounds really unrealistic when you create new data set, right? For example, they don't post things in batches sometimes, or they probably don't monitor closely to the quality every batch. So when you create a new data set, in practice, you post your data in batches, and for every batch, you go into the data, go and see what's going on, and you identify some low-performing workers, and you probably remove them from future tasks, right? And the people don't really do that. And sometimes they do things, for example, some of the study actually use the Go label for the entire data set to remove low-performing workers. For their purpose, it's probably fair because they want to remove outliers, but it's not realistic for when you build a new data set, you use the Go label for the whole data set to remove workers. And some design selection is also a little bit weird. For example, some of them only use master qualification from Mechanical Turk, which there are some literature saying it's not a very effective way to do things. And of course, again, we agree that it's probably because they have a very different research focus. They focus on individual worker performance than the more holistic view of crowdsourcing pipeline. And of course, some of those studies using existing crowdsourced data set is already out there. And of course, there's a concern about data contamination, right? If it is possible, the language model already see those papers. So that's a complaint from crowdsourcing experts. So as an academics, when you complain about something, what do? You write a paper about it, right? So, and as a crowdsourcing expert, any of you who did crowdsourcing before, you know, crowdsourcing is not just about crowd workers' ability of labeling data. It's actually an ecosystem, or at least a pipeline. So again, this is also a simplified version. You first need to figure out the data source. You need to download the data, obtain the data. You need to clean the data or pre-processing the data in some way. And you need to figure out which platform you are going to use. You need to figure out how to instruct or train your workers right in your interface, or you want to hire them in-house. And you also need to figure out your tasking, right? So what I'm going to label, what's the instruction, and what's the meaning of those labels. And after all that, you need to figure out an interface. And very likely you need to iterate, right? You need to kind of figure out, okay, I'm going to annotate this. So this is the interface and this is the instruction. It's an iterative effort. And when it actually comes to data annotation, you need to basically monitor the quality and you need to pick the low performing workers and probably filter out them. And you need to communicate with workers and also make sure you pay them fairly. And of course, often enough in practice, if you are going to label 10,000 stuff, you probably need to do things in batches. You post 1,000 at a time and you look at the data closely, you make sure everything goes right, because in reality, that will cost money. And that's only happen during annotation, right? So after annotation, you also have this separate effort to clean the label you get. And after that, you probably also need to aggregate label in realistic setting. Usually for every item, you probably want to collect multiple labels and then you want to aggregate them in some way. And eventually, after all this effort, you get your label dataset. That's more realistic view of things. So because of that, like I said, when you're unhappy about something, you do good research and you write a paper about it. So in CHI, which is a top tier HCI conference 2024, we published a paper basically argued, well, let's compare ChatGPT with crowdsourcing pipeline instead of a single crowd worker's ability, right? And this is a task we pick. So basically, we use the same annotation scheme. It's called CODA-19 dataset. And in that dataset, you basically split the paper abstract into sentences, and you classify each sentence into 5 different labels: background, purpose, method, finding, and other. Right, and that's the task. And we pick this task because it's kind of balanced, the difficulty level kind of balanced in the right way. It's not too hard, right? It's for some tasks, we kind of know it's just very, very hard, even for humans. And it's also not too easy. So it's not too easy, like 2-class or 3-class sentiment classification tasks. So, and we also know based on prior literature, this is not very easy for Mechanical Turk workers. A prior team try to do the same task with Mechanical Turk workers, and their accuracy is around 60 to 70%. And we basically redo it with more sanity check and with more serious quality control practice. And in our original dataset paper, we reached to about 80 to 85 accuracy. So we know it's not an easy task for Mechanical Turk workers. And for this particular paper, like I said, because the data contamination concerns, we really need to create a new set of data for this purpose, right? So we cannot sit and just complain about things without doing any new data collection. So we did collect 200 papers published after 2022. And we did ask a biomedical expert who is a faculty at UCSF, say, I know you are great, but can you sit down and label these 200 papers for us? And we use that as a gold label. And this data was never published on the internet, and it was entirely new. So we get rid of this concern of data contamination. And because we already published a data set before about this, so we have a well-established instruction. And the biomedical expert who also kind of participate in the original data release, so she is really an expert for this data set and instructions. So that's the task we pick. And in the actual data annotation study, we use Mechanical Turk, and because this is a scientific exploration, so we kind of push it a little bit. For every item, for every sentence, we collect 20 labels. We ask 20 crowd workers. In practice, probably 5, 7, 10 is enough, but we just want to know. So we actually collect 20 different labels from 20 different workers. And these are the worker qualification we use. And in this particular study, we tried 2 different annotation interface, 3 different label cleaning strategies and 8 different label aggregation methods. So if you combine everything, it's 48 different combinations. So I think the slightly more crazy part is the interface part, because in one HCI literature, we kind of know in crowdsourcing tasks, interface matters, and different interface will give you different results. So what we did is that we have 2 versions of interface. One is done by my PhD student, and the other is done by me. And the student is intentionally to kind of make an interface that is relatively simple and just have the same instruction, but with very little visual feedback, and basically don't have anything that you can overview your labeling results. And this is the interface. Okay, so this is interface. You can see this is the instruction, which has a lot of content. And the actual interface is pretty simple. You just go and label stuff step by step. So this is the interface I created for the original code-annotating data set, which is a lot more complicated. It has more visual feedback, and it also allows workers to review the label at the end of the interface. And this is how it looks like. You also have the send instruction at the top, and you can see every sentence is basically in a separate row. And when you scroll through, you can kind of click through them and you see the visual feedback, so you know which one you're labeling. And you also get this like red box highlight and different color label. At the end of the interface, you can see the overview of your label. So if something looks very, very wrong or different, you can kind of catch it early, right? What I'm saying is this is just not a prettier the interface. It actually has some function that can help workers to label things slightly better. And I promise you, there's a point after that there's a reason we are watching this, right? And this is the label cleaning strategy. So in our particular setting, label cleaning strategy is really to decide if in some batch you decide to remove one workers, what do you do with the label this particular worker already gave you, right? So for example, this particular low performing workers was kind of identified at the batch 3 is a low performing worker, and what do you do with the label he or she provided? And there are basically 3 ways to do it, right? So 1, you just don't do anything, you keep everything. And 2nd, you can just remove all the labels provided by these workers, or you can just remove the last batch. So that's a high level kind of strategy we talk about here. And how do you identify low performing workers, right? That's a big question. So the real answer is we do it in a very messy way. So in a real world setting, when you are creating a new data set, you don't have Go label for the entire data set. What do? What you can do is just go into each batch, use whatever signal you can get. In this case, I believe we use how often this worker agree with the majority vote. If there's a worker kind of much lower, has a much lower chance to agree with the majority vote than average, maybe something wrong, then we go into the data and see if there's anything wrong, right? And for this purpose, I also asked my student, just try to be realistic, right? In realistic data collection effort, usually the requester, often is PhD student, need to sit down, label a small set of Go for each batch, and you use that small set of Go label to do quality control. So that's what we did. For every batch, the student annotate 10 items, use that to help you identify lower performing workers. That's the data cleaning. And finally, data aggregation. So data aggregation means when you have multiple labels for one item, for example, in here, and you really usually have a way to decide what is your final label. And the easiest way to do is probably majority vote. And in here, you basically use majority vote to decide, okay, final label is finding, right? And of course, majority vote is just like a baseline approach. And in practice, there are a lot more things you can do to hopefully outperform majority vote. And in this study, we use this open source toolkit called CrowdKit, developed by the company called Toloka. And we do have some communication with them. So they kind of explain to us when the documentation is unclear, is that what this algorithm do. And we basically try 8 different label aggregation algorithms, including majority vote. All right, so after all those talking, so we try many things, we try different variables, and this is the best setting we get. Basically, the best setting is you just remove all the labels from low performing workers. You don't keep any of them. And the best setting comes from the advanced interface, the one I created. And this, the y-axis in here is accuracy of the label, which will compare against biomedical experts label I just mentioned. And the x-axis is basically how many labels you use in aggregation. And of course, empirically, more labels you use will result in the better accuracy. And 8 different lines means 8 different label aggregation algorithms. Okay, this is the result from all this hard work. However, this is GPT-4's accuracy. And initially, right, the motivation we did this study is that no, they did it wrong. We want to do it right. So let's just putting all our knowledge and effort and expertise into this, make sure we do everything right, ethical payment, small batches, quality control, aggregation, data cleaning, interface. And still, we didn't beat GPT-4 in this particular setting. Of course, we know this is just one case, right? We didn't try more tasks. This is just one thing we try, right? But in this case, we failed to beat GPT-4. Then what do? So none of the 48 different combinations beats GPT-4, and we got close. We got very close, right? Some of them is actually pretty close, but we didn't beat GPT-4. Yes.
Out of curiosity,
yes.
Just a fun question.
Yes.
How much did it cost to get the upper rightmost trading point, and how much did it cost to?
Can I give you that question? So we did, yeah, that's a fair question. So we did report that in the paper. It's a lot more expensive to use crowd workers. Yeah. It is true. Yeah. And it's even cheaper to use GPT-4 now, I think, right? So it is true that it's a lot more expensive. We did have the cost in the paper. Yeah. Okay, let me.
I have one more question.
Yes. Oh, yes.
Yeah. What happens if you add GPT-4 as an additional crowd worker?
That's exactly what I'm going to say. So all this result, right, is kind of asking this question: do we still need humans in future large-scale data annotation, or like when do we need them? No, how do we need them, right? So exactly what we did is this. Good question. So basically, the most straightforward thing when you already collected a bunch of crowd labels and you have a very good GPT-4 label, the most straightforward thing without changing much is just to add that label as one worker, right? And that's exactly what we did. So this is the result. This is the accuracy, right? So again, we have 8 different aggregation algorithms, and the blue line is the accuracy. Blue line is the accuracy before adding GPT-4. And the green line in here is pretty sad. It's the GPT-4's accuracy, okay? And the red line is the accuracy after you add GPT-4. Again, red line is after you add GPT-4. And you will see that in most cases, actually in all cases, you will actually improve your accuracy. That is good. And we do see in aggregation algorithm that sometimes you will introduce some weird drop or weird kind of turbulence here. We didn't really know why. We tried this several times and it's still the same. So probably something interesting there. But most importantly, this too. So we actually beat the original GPT result in 2 of the settings, right? In here, it's not by a lot, but we did beat GPT-4 alone. Yes.
Is this common in like the crowdsourcing literature to use this one coin Dalit, Skeen, and Mace, or is this kind of like rare methods people wouldn't have thought of using?
So in literature, it's actually common. I think OneCoin and Mace are relatively popular in this area. That is true. But my sense is that often enough people, if they don't care, they probably just use majority vote. Okay. But again, we didn't invent this, right? This is like toolkit, so it's not very hard to do. Okay. And Mace and OneCoin is actually a very well-established method. Okay. I think May's paper was published by Dirk Harvey actually 10 years ago, and the code is still out there on GitHub. So Yes, so they are not very hard to do. And oh yes. Oh, what do you mean? The aggregation? Oh, so the aggregation algorithm will basically learn the weight. The input to the algorithm is the same. We didn't give any extra knowledge on top of that. But you can, of course, you can argue that the label cleaning strategy is kind of a working knowledge that we inject to the process, right? Because you empirically kind of guess, oh, this worker is not good. And then you remove them from the process in some way. You can argue that is a knowledge, but that's about it. We didn't inject more than that to the aggregation algorithm. Right. Yeah. So basically, you are saying that because if we have a pretty good knowledge about how good this annotator is, we can probably take advantage of that and do some smart combination. We didn't do that here. Technically, yeah, we can probably, for example, if we can estimate the accuracy or something beforehand, and we trust that a lot more than this, yeah, we can, but we didn't do that in here. And the interesting part, I mean, this is kind of positive example. A positive result is that two aggregation algorithms out of everything kind of reach even better accuracy. And the interesting bit here, it only happens in my interface, in the advanced interface. It only happened in the good interface. It didn't happen in my student's interface. We take that as a learning. So, yeah, so there are some, in the paper, there are some discussion about why maybe, so if you just look at accuracy, you didn't see the very big difference between my interface and my student's interface, but there are probably something more nuanced there. And we will have some discussion, but takeaway, interface kind of matters if you actually care about a few last point of accuracy. All right, so at least there are something we can kind of hope for. So there are some hope, right? So what's the, yes.
What is the interface that people observes? Is it that text only, or is it the same visual interface, that graphical interface?
That's a good question. So back then we just give it instruction in text. So it does not see the, so I guess you're talking about the interface as an image or something like that, right?
Yeah.
No, it does not have that. So that's a fair point, right? It's like probably that also gives you something, but we didn't try. I don't. Yeah. Yes.
So in this case, you aggregate results between one language model and many human annotators.
Yes.
You thought about what would happen if you just tried sampling many completions or labels from.
Sorry.
What happens if you sample many labels from one model, or you mix labels from many different models?
Yeah, that's a good question. We didn't try that in this particular project, but yeah, there are some other people's work did try that, and in some cases, yeah, it could help. So in short, it could. So this paper was like 1-2 years ago, right? If you do it today, it will probably be even more brutal than now. But yeah, there, at least back then, this result gives us some hope that when you have human labels and you have enough of them and the quality is not bad, if you blend them with language models label in some way, we don't guarantee what way it will work, but there are some hope you can improve the accuracy further, right? That's the, yes.
So without even including the ChatGPT, did you already have higher accuracy if you're advanced?
Yes. A little bit, yes, a little bit, not too much, but yeah, a little bit. Yeah, you can see. I think my impression was that you can see the accuracy increase, but you won't think it's that significant. It's just a little bit. Yes, but yes. Okay. All right, so then that kind of this is the result of the project, right? And that kind of lead us to this question of the key kind of elephant in the room that we want to think about nowadays. To be fair, we don't know the answer, but what roles can human play in future large-scale data annotation? Especially, of course, especially for tasks like this, it's probably not too hard for language model. Language model can do pretty well. And what should we do? Do we still need humans, and when do we need humans, right? And these are 3 sets of arguments. I think it's relevant. So there are some arguments about why we still want to have humans in data annotation. One is, of course, the quality argument, and the rationale for that is that some tasks is still very hard, or at least harder for language models than to humans. So you still need humans. It can be crowd workers, can be experts to do the annotation, or at least to clean the data for you, because they are still better, right? So that's the argument 1. And the second argument is probably the diversity argument. And the rationale behind that is basically humans are often kind of different from each other, and humans differ more from each other than, say, between language model agents. That's still often true, right? In many literature, we kind of know synthesized data are probably less diverse in some way than human user-generated data. That is still true. And if that's relevant to what you want, maybe you still need humans in the loop. And the third argument is I call personalization or user agency argument. In some case, you still need user input or user to tell you what they want. So the argument is that the user are the person who can actually tell you the nuance of what they want, right? So that's the 3 sets of argument, like why or what role do we need humans in data annotation? And for the first 2, we have in kind of some NLP work. And so today I kind of want to focus a little bit on the third argument, which is the personalization or agency argument. It's like, okay, what does this mean? What does this mean? So this is traditional crowdsourcing pipeline. You can see that you have a human requester, researcher, developer, decide the data, decide the label scheme, and you send everything to crowd workers or labelers or PhD students to do the labeling, and then you get the label data. And in a version of future, maybe it will be things like this, right? So you prompt language model, and language model through some software do the labeling for you, and you get the label data, right? So that's many people are actually trying to do in this space. Well, I would probably argue that in this pipeline, you still have a human there. You still have this human requester, researcher, developer prompting your language model to do data annotation. And one thing they can do now, which it was very hard or much harder to do, is to quick iterate, right? Because in crowdsourcing world, to quick iterate, it's almost impossible. Even you have in-house annotators, it's just very slow to kind of go and see the annotation and then revise your data or revise your label scheme. People do that. It's just kind of painful and slow to do and expensive, right? But now with language model, what you can do is you can do this quick iteration. You can just say, hey, language model, annotate this data for me in this way. And you look at data, you eyeball the output, and then you just revise your prompt and redo that again. So it can be done almost instantly, right? And increasingly, we see people do that without using Go labels. So basically, they eyeball the data, eyeball the output, say, okay, this looks good, and then they just go with it, right? It sounds surprising to some people, but it is true. It's that in our paper, we do have some pointers. People do this kind of vibe labeling thing without using Go label to evaluate what the outcome is, right? So we are not saying it's a good practice. We are just saying people are actually doing this. And we are not the only person who saw this. So this is a paper from our friends. Some of them, we actually know some of them, from Google last year, December last year. And basically a higher level takeaway is that the data curation practice kind of moved from this heuristic first, bottom up approach to insights first, top down workflow, right? So at very high level, that's probably not a bad thing, but do you really not need Go labels? So in quality control literature in crowdsourcing, there are basically a lot of papers tell you you need to use Go labels. And this is just one of the most recent one. Go labels in data annotation process can help you to do quality control in many ways, can give you signal to identify low performing workers, can give you signal if something systematic go wrong. You can even use Go labels to train your workers or you can at least use that for attention check, right? If they just click random things and it will show up if you embed Go labels in your annotation task. People kind of know that for a decade already. Will this time be different? Do we really not need Go labels in this era of large language model? We don't know. So again, as a scientist, when you are not sure, we're unhappy, you complain, you write a paper about it, right? So in 2025, this year at Kai, we published this paper, Prompting in the Dark is the catchy title. So in this paper, we kind of more seriously define what is this prompting in the dark practice. We think people begin to kind of label data in this way. Users' understanding of the data and their desired label scheme evolve through their interaction with language model and its output, rather than sit down and manually do your homework, right? So that's basically how we define this behavior. And of course, one key item here is understanding, because that's kind of also, we believe that the understanding also evolve over time when you actually do iterative prompting with language model. All right, so the prompting in the dark process roughly look like this. Initially, you have a prompt, and in your prompt, you have different components. You have task, context, you have labeling rules, and from time to time, you have a few Go examples we call Go shots. That's the first step. You kind of compose the initial prompt, and then you probably sample a small set of data from your full data set, because in this process, you want to eyeball the data. It's impossible, not impossible, but it will take very long if you want to eyeball 1,000 items every iteration. So likely you need to do some sampling. And then you use your prompt to label that data sample, right? And you get your predicted label. And for language model, you can also ask language model to give you explanations, like why this prediction looks like this. And finally, user just observe the data sample, explanation, and the labels, and use that to revise their prompt if they're unhappy. And of course, this can be done iteratively, right? So you can kind of iterate this relatively quickly as compared to crowdsourcing days. That's the process. So we built a prototype tool. So we still need the software to actually perform the labeling. We create a prototype tool called Prompting Sheet, which is actually a Google Sheet plugin. And in this sheet, you basically have all the function at the sidebar, because that's a constraint that Google Sheet enforced on us. And so every kind of function or buttons can only be shown on the sidebar. And each of the tab or the sheet in this Google Sheet is basically point to a different function. You have a sheet for the whole data set. You have a sheet for your rule book, basically explaining every label. And you also have a sheet for task context. Is that what is this data? Why I'm labeling this data? And you also have a separate sheet for we call shots. It's like a small Go label shots you want to use and include in your prompt, right? So that's the idea. High level idea is basically to stick with some interface that user kind of already know, so they don't need to figure out the interface from scratch, because the workflow itself is already kind of complicated. So we want to stick with some more familiar interface, right? And every time you send a task, you basically send annotation task. We copy the whole thing, the prompt, the label, the data, and put it in a separate sheet, so that you can, if you want to navigate them, you can kind of go back to see all the labeling history. That's a high-level idea. And this is a short demo video. I hope we can
answer a few questions about the annotation task, such as the purpose of doing this annotation task. How will the user use the annotated data? What is the source of the data? What is the data size? Those answers are regarding the Twitter sentiment task. In the rulebook sheet, there are columns for label name and rules for label. We can list the labels under the label name column. For the Twitter sentiment task, the 5 labels are extremely positive, positive, neutral, negative, and extremely negative. We will need to provide a definition for each label under the rule for label column. This step is required. After we imported the data and defined our label rules, let's sample some data. In the reality, sometimes the entire dataset is too large for users to review in full. By selecting a subset of data instances for annotation, users can focus on a manageable portion of the dataset, allowing them to gain overall insights into the annotation task. You can do this randomly or sequentially. Random sampling selects a set number of data groups at random, while sequential sampling picks groups within a specified range. In these two examples, the data instances on the left are randomly sampled from the dataset, while those on the right are sequentially selected from the dataset to process in batches. Let's randomly sample 3 tweets as an example. With our data samples ready in the working data sample sheet, we can scroll down to the button of the interface. Here, you have the option to choose whether to display LLM explanations in the annotation results. After making your selection, click Start Annotation. Prompting Sheet will combine content in the context sheet, rulebook sheet, and shot sheet to create an instructional prompt, and then use the prompt to instruct LLM to annotate the data. The system will create a new sheet to store the data sample and the label results for the specific annotation task.
All right, so that's the demo of the system. And we also have some steps you can use. Basically, if you see a label that you really like, you can keep it and add it to the Go Shot sheet. And you can also do it manually. Again, this is a Google sheet. So if you really want, you can even like manually create a new example and what label you think this should be and manually add that to the sheet. So, So basically, we call this behavior prompting in the dark. Remember everything I just demoed. I didn't mention anything about evaluation, right? So because we want to test this behavior, the system itself did not provide any guidance. We don't use Go label to tell you the accuracy, tell you the MSE, or give you any guidance. It's just because, again, we want to see how effective it is. And we call this prompting in the dark. Is almost just like you are driving and the only thing that can guide you is basically your eye. You just look at the data and say, okay, this looks fine. And when I show this to my student argue with me a little bit. No, in this photo, you have the transportation system. Road has a lot of rules come with them. Sure, it's in the data annotation. You also have a lot of rules, right? You have the format, you have the label is a very constrained space, and that is also true. And again, this is visual metaphor. So the research question we want to answer is that how effective is it for human to actually do this? Although many literature in crowdsourcing, in human computation, even in software testing tell us you should use Go labels. You should use Go labels. Will this time be different, right? So because we don't know and we want to see that. So this is the user study, and the user study is a little bit long. So you have an onboarding task, and because this is kind of a new software, so we have a tutorial task, ask them to label something different. And in the main task, the language model we use is GPT-4o, and we basically ask everyone to at least do 4 iterations. They can do more, but they need to do at least 4 iterations. They create a prompt, change the prompt. They create a prompt, they label the data, look at the output, and revise the prompt. They need to do this at least 4 times. And the data is the same as shown in the demo video, is the COVID-related tweets. And it is true, probably we focus a little bit more on the personalization or user agency aspect of it. So we think everyone for this type of sentiment task, everyone probably have a slightly different standard and want to see if this is the same person who control a language model and the same person who actually create a Go label, how would that look like? How effective it is? So we ask participants to label the Go label at the end of the study session. So hopefully by then they already kind of have slightly better understanding of this data and this label scheme. And at the end of the study, after they finishing using our system, they sit down to label 50 tweets, and we use that for evaluation. So basically everyone has different goal, and they basically have a different kind of standard or their own kind of ways of expressing sentiments in COVID-related topics. And the evaluation, right? So basically it's a sentiment task. So there are accuracy and mean square error. And when it comes to accuracy, of course, the higher is better. And when you use accuracy, it's basically a hit or miss situation. And you only care if it kind of exact match. And if it's not, then it's a miss. And for mean square error, we actually care about the distance of the prediction, the actual goal label. And so the larger is worse, lower is better, right? And this is the results. So surprisingly, I talk about a lot of negative results in this talk. So prompting in the dark, at least in our study, arguably it's a smaller scale study. The accuracy and MSE doesn't really change much. If you focus on average accuracy, it did increase a little bit, but it's just not very significant. And if you look at MSE, that basically doesn't change. And if you break it down, remember we have 20 participants. If you look at their accuracy changes over basically the 4 iteration, including the initial prompt, so you also cannot really see a very systematic trend. And initially when we did, yes?
How did you evaluate the change?
The change?
How did you evaluate the change?
Oh, so so you mean for this one?
Yeah.
So we do have a significant test, and we basically compare the because they all share they all use the same set of data. The data is the same, so they kind of pair in some way, right? It's just a label is different, so we can translate that into right or wrong. It's like 1 or 0 situation, and you do significant test that way. Yeah. So again, the data, everyone uses the same data, just the goal label is different across different participants, right? And so you also don't see many kind of trend in here. Well, that's kind of surprising. That was surprising to us. Initially, we thought at least we will see some trend and people should at least improve it. But that turns out not to be true. And okay, and then we think, well, maybe there are some variable you can change to improve this process, right? But if you look at this process, there are only very little kind of generalizable variable you can explore. So obviously it's just these 2, right? So either you show the explanation or not, or for every iteration, you show more samples, right? So intuitively, maybe you see more samples, you can get more insight, and probably your iteration will be more effective. And so that's what we did. In our study, we actually have 2 variables. Each of them has 2 conditions. So for explanations, underlyingly, we always ask language model, give us explanations. So the performance-wise, it should be the same. It's just the users can see or not see that explanation. And the other variable is the sample size. We tried 10 and 50. We did think, well, that's probably too little, too few. But practically, if you want to really seriously look 100 items, every iterations, that's a little bit too much. We did try a little bit that in some of the pilot. So this is our final experiment setting. So not too surprisingly, if you look at more samples every iterations, the blue bar is when you look at 50 examples every iteration, and the brown bar is 10. And this is the differences, the accuracy differences as you compare to the initial prompt, right? So the blue bar basically systematically increase the accuracy, at least it's positive. It's not by a lot, but at least it's systematically positive. And the MSE is also often lower. So basically, when you look every iteration, you should probably read slightly more example than 10. And we agree that 10 is probably obviously too little, but that's what we got. And more interestingly and really surprising to us is probably this result. When you show explanations, the performance actually dropped. So basically, there are 2 settings. The blue bar is when you show explanation. The brown bar is when you not show explanation. And when you not show explanation, the accuracy is actually increased, right? So this is compared to your initial prompts accuracy. But of course, the signal is more mixed in this case. We didn't see any consistent evidence in the MSE case, but it's probably when you do this in your own setting, probably think twice if you want to show the explanations. And one potential explanation is that we, of course, focus more on the personalization side. So everyone should have slightly different preference. That is slightly different than when you have a centralized truth, right? So if you are going with some label task, you actually have an expert you rely on and you assume there is a good or bad or true or not true answer. And that is slightly different, right? So, but it's just when you want to show explanation in this kind of process, probably be careful. And we do a little bit more analysis on why this happens. So we kind of one hypothesis is that maybe it's the optimized setting just move people to edit more, and we did try that and it turned out it's true. So the monitor I'm looking at in here turns off. Is that normal? So I hope you can still see the monitor here. So the optimized setting basically is systematically move our participant to edit more, so it's less similar to their original prompt. And that's not causal relation, that's just correlation. So maybe that's a reason, but we don't know. That's just one observation we can do.
Try moving the mouse.
Where's the mouse? Okay. Oh, wow, technology. All right. And before we go, right, so one, this result kind of gives us some hope, right? Maybe it's just the participant did not get enough insight to motivate them to edit their prompt. And when they do, it actually results in better outcomes. So that's probably one explanation. We should do more to study this, but that's one direction we are thinking. And of course, before we go, there are dSpy. I'm not sure if you try this. We did try to use dSpy too. dSpy, part of the function is that it can try to optimize your prompt to improve the outcome automatically. So we did try that in different points of the iteration. In our case, it did not help that much. And the possible reasons could be that the gold labels, the gold shot collected in our study was very few. It's usually 5 to 10. And that's probably not enough for the code to learn anything. And it could also be that the LLM we use is already kind of strong. But at least in our setting, it did not help, right? So, okay, that's the second project, right? So what do we learn? Well, Go labels are important. We already know that, but no one is listening. So Go labels are important again in the era of large language model. And humans are not very good at prompting in the dark, at least not without Go labels. And human involvement can probably help annotation, but the approach matters. This is particularly interesting to HCI people. If you remember, in the first project, only the advanced, the better interface result in improvement over GPT-4, right? Well, what does that mean? So if you actually care about last few points of accuracy, maybe you need to pay some attention to interface. That's probably one takeaway. And also, what's next? I think, again, evaluation. The role of Go labels often enough is for you to evaluate your prompt, and that is very important. And you have a small set of high quality, reliable Go also can help you to make many decisions. Remember, in the first project, we have 48 different settings, and only 2 of them can outperform the GPT-4. And if you have a small set of Go label, that can kind of guide you, oh, these are the 2 settings I should go after if I want to scale this up. And what we think is automated support matters, right? So there are some systems out there try to give you some feedback even without Go label. For example, you can ask language model to evaluate your output and give you some feedback. So we do think automated support kind of matters in this process. And at Mask last week at Penn State, one student actually tell me, well, how about education, right? How about we educate people to write better prompts? That could also be a direction. And in this talk, I intentionally not touch on this kind of elephant and other elephant in the room. Is like, why do we still keep creating NLP or AI data sets, right? So the way people created data set kind of changes over the past 2 years, maybe. So in old days, so as soon you are creating a data set, you will definitely have a training set, you have a validation set, you have a test set, and you create this data set with the assumption someone will take the training set to train a smallish model like BERT model or some model, and then test on your test set and probably use validation set to fine-tune the parameter. That's the assumption. Is that still true in 2025? Right? Many data sets, actually not many, but some of them don't have data split. Some of them only have test set, right? So nowadays, in some case, people just create really, really difficult and of course, really, really high quality test set to test if language model can do this, right? And so the paradigm of building data set also changes. And why do we keep creating data set becomes a realistic question. Surprising. But I think that's also a very interesting thing to think about. Before we wrap up, I want to mention one thing we are trying to do, which is a little bit weird. So because we already have a lot of crowdsourced data set, right? And one complaint about crowdsourced data set, like I said, is the diversity, right? So if you just, so not complaint, it's like one feature of crowdsourced data set is it's pretty diverse. And if you use language model to synthesize the same data set, it's likely you will get less diverse version of the data set, which good or bad depends on what you want. So in this particular paper we published at ENLP last year, we tried this thing. Basically, we still crowdsource data set. This particular data set is we tried to ask crowd workers to write news comments. We show the news. This is a news article. Please write comment for this news. But please embed this logical fallacy in your comment. Can you write a comment that has this logical fallacy, right? So we try to construct a data set for logical fallacy detection and classification. It turns out it's a very, very difficult writing task, right? Read this news, write a comment with this fallacy. It turned out it's probably a little bit too challenging or takes too long for Mechanical Turk workers. So what we did in this project is actually in the interface, right? In the interface, we actually just give them large language model support, right? So in the left bottom corner of the interface, we have this, so they can write. So we ask them to write a few words in here to begin with, and they can click this button and set get suggestion, and they can get first part of this is the suggestion, it's like higher level suggestion for you. And we also provide a example for you. So of course, on the interface, they cannot copy paste and they kind of need to read and type whatever is there. And it turns out when we add this function, we get a lot more response from Mechanical Turk. And we also do quality check or something like that. The data set quality is actually pretty good. It's actually a lot better than we expected. So, and we currently, what we are doing is, of course, try to use language model to kind of replicate the entire process. How about we just build a data set without crowd workers in the loop? Because now this part, the initial part, and the basically final revision of the comment is still done by crowd workers. And what if we just replace that with large language model? It turns out if you do that, if you replace this with language model, the diversity kind of drop drastically, right? We try to synthesize a version without human. It turns out it's just much less diverse. And of course, you can argue maybe when you have scalability, it can still kind of compensate this. Depends on what you want from this. But that's one direction. If you are you are creating a data set and language model synthesize give you very, very low diversity, maybe thinking about ways to having crowd workers in the loop, to use them as a seed or as an ideation phase, and probably that can increase the diversity of your data set. All right. All right, so this is my lab. Thank you for inviting me. I'm having a good time. Thank you very much. Any questions? Any question from the Zoom call? Yes, Kevin.
I have a business question.
Yes.
So with people thinking LLMs can do a good job, and you also mentioned that Google paper as well. How do you think the the industry would change, like how would Mechanical Turk or Prolific or other companies? Do you think there's going to be a change in this business?
That is a tough question. So I think so it was already true before language model era that Mechanical Turk tasks became harder and harder over time. I guess what I'm feeling right now is that the ChatGPT kind of make it a lot worse really quickly, right? So because for example, our first project, if you don't care about the last 1 or 2%, just go with ChatGPT, and that will basically require both requester and workers to be much better at their job, and that will probably change many dynamics in the crowdsourcing or data annotation business. That's probably one. And two, I would imagine a lot more focus will be from initially, like in early days, we talk a lot about how to use AI to help human annotation. And probably now we'll shift to the other way around, is that a lot of focus will be how to add human to help AI annotation. I feel like that's probably another shift. I don't know about business implications, sorry. Yeah, but that's an interesting question to think about. Yeah. Yes. Any questions? Yes. Yes.
I could make a model performs better and better and sorry, better. So after 10 years, like
After a few years.
achieve very high to the point that I'm not sure, but maybe no very powerful and no need human annotation to train the model. If it can achieve that one.
Yeah.
I can see some points from your slide that maybe we still need human annotation for evaluation.
Yes.
Yeah. See why the machine can still perform the same what we want to do. And I want to see, do you have other insights on this one?
So basically, I guess what you're asking is like, why do we need data set, right? It's like in 5 years, if language model is like super powerful. Yes, and then why do we still need data set? I feel so. That's a tough one. So I did have discussion with friends working on developing large language model about this. I guess for now, if you ask me, this is like a high quality, reasonable size data set. Even today is still probably the best way to constrain your model behavior. So if you have a business and you have enough data in this domain and you want your model to behave in this very particular way, probably you still need a data set and reasonably sized data set for that purpose, right? And that will be true for certain period of time. I guess another question along the way is, of course, like in 20 years, right? And I don't know, is it in 20 years if we have like super powerful GPT-20 and can just do everything? I'm not sure I'm convinced, but if that happens, I don't know. I think if that's the case, we'll probably focus entirely on evaluation. That's probably it. But I don't have a good answer to that question. Yeah.
How do you think the relationship between human and the machine, and also besides beyond the annotation, we also have the definition. But how do you think the relationship, and how do you think the role of human?
Well, that's even bigger. So that's I guess the reason why we're interested in this prompting in the dark is because one direction I'm interested in is user agency question, right? It's like I do a lot of work in writing assistant, and one line is creative writing. And I am personally not very interested in like a fully automated story generation pipeline. I'm interested in how language model can or cannot help very good writers to write very good things. And for that, I'm curious about what writers want to say, what kind of story they want to tell. So for that, you probably still need human in the loop. And to me, so there are, let me answer this question without answering this question, right? So in old school HCI, there's a debate between direct manipulation and software agent, the very famous debate from Ben Schneiderman and MIT professor Matt. Sorry, I am terrible at remembering names. And there is a very famous debate 20 years ago about that. And Ben is a very like strong opinion about AI or computer should be tools. And I kind of feel like I probably, if you force me to choose, I probably more on that end. So I like to think about language models still as a tool, even it's a very, very powerful tool, it's still a tool and it can help you to tell your story and do your thing. And for that, you still need human because what I care more is like what the human want. It's less about what machine can do. It's not entirely not about, but yeah, it's less about what machine can do. That's probably my take. I don't really know the answer to that question, but that's a great question.
I looked it up.
Yeah.
And the MIT professor is Patty Mays.
Yes, Patty Mays. Thank you.
So she basically invented collaborative filtering.
Yes.
She had a startup that was like making recommendations of movies and products and things like that based on her past behavior.
Yes. Thank you. And their debate, they have the transcript and they publish the entire debate in the transcript. So you can find the entire debate online.
1997.
Yes, exactly. 20 years ago. Oh, 30 years ago. I feel old. So it's 30 years ago, but it's still very interesting, right? So for example, in that debate, they talk about the future of natural language interface. And one of the argument is that, oh, it's just not very good. And nowadays we talk to Siri, talk to Alexa every day, right? So things change and some core argument is still the same. I think it's a very interesting read. You should probably take a look. Thank you very much. Any question from the Zoom call? I cannot see them from my monitor. No? All right. I guess that's
question.
Yes.
All of this was English, right?
Oh.
Like, yeah, I know. This is probably an open one that I don't think anyone's working on.
Yes.
Do you have any indications how well this would work in other languages? Because I don't think GPT-4 would be quite.
That's a good question. So Mechanical Turk is still heavily I know CCP also have like this kind of translation paraphrasing data collection,
Right.
but still, even today, Mechanical Turk is still heavily English focused. So one, to replicate, let's say if you want to replicate this in different language, you need to find a platform that you can hire good people, and also language model performance varies, right? So,
Right. So I mean, the language models are worse, and it's harder to find good human annotators. So
yeah, that's a good point.
So
Yeah.
which one do you think would be better? Like, it's still a guess. It's not a fair question.
So go back to the comment about money, right? You should probably try language model first because it's probably easier to get an answer. So we also, it's like earlier days, I also tried to do crowdsourcing on Mandarin Chinese. Mechanical Turk, it can be done, but you need to put in a lot more effort. So for what you want, you probably need to find the right platform for things. Yeah.
We must have any other pressing questions. Let's thank.
Any other questions about future of crowdsourcing, data annotation?
Thank the speaker for a nice talk.
Thank you very much. Thank you for having me.